Good afternoon, ladies and gentlemen. I'm Luc Dini, chairman of AAAF Sigma 2 Technical Commission, and I have the pleasure to introduce the webinar free on UAP observables, which takes place on July 2, from 2 in the afternoon to 6 in the afternoon. What about AAAF? AAAF means Association d'Aéronautique d'Astronautique de France, and it's a scientific society which is registered under French legislation and which is covering many activities related to the research on airspace, air phenomena, aeronautics, astronautics. And this scientific society includes activities related to international conference on various topics: space, propulsion, missile defense, space transportation, and so on and so on. At the same moment, we have also a technical commission with participation of experts in various technical domains. And among these technical commission, the Sigma 2 Commission takes activities and conduct research on UAPs. What about UAPs? UAPs are real phenomena with remarkable observables. In the optical domain, in the radio frequency, a lot of observations are made and some are recorded. Radar and electromagnetic sensors are very precious to try to observe and register the UAP observables, kinematics, but also signature. And by combining electromagnetic sensors, optical sensors, we can try to approach these UAPs and to know better their features, try to understand what it is, how it can fly or move in the airspace, and so on. Today, for this webinar, we will address two themes. Cases analysis. What about the observables related to these cases? What is our approach to understand what is happening? And another subject will be related to the observation itself, the techniques used to capture information on the UAPs. This webinar free, because that's the first years that we are performing this webinar, has been supported by a lot of members of the AAAF staff from the Sigma 2 Commission, and also has invited contribution of various societies working on UAPs from Sweden, from the US, and so on. So you will have the details of their participation, their bios, and the abstracts part of the program. So this program takes place with first session, as I said, on cases analysis, about 20 minutes each session. The first one will discuss the Stephen Weylight's phenomena that happened in 2008. Mr. Robert Powell, who couldn't make it directly to be present among us, has presented this paper last year. And this is important for us to discuss this approach, this analysis from the SCU, because on our side in Sigma 2, thanks to the data provided by the SCU, we conducted an analysis in depth of this case. So after Mr. Robert Powell presentation, we'll have a presentation prepared by Brigadier General retired Jean-Marc André, was a fighter pilot in the French Air Force, Mr. Philippe Chopin, a specialist of radar analysis, and Mr. Emmanuel Plichon, also specialist of air defense. They conducted analysis on different cases, and Brigadier General Jean-Marc André will summarize the analysis, past analysis on Stéphane Weil, but also Jersey, and we will make commenting also on the analysis performed some years ago on the Cougar case, where we had infrared sensors plus radar information, and also on the case coming from the Puerto Rico airport. Then we'll have some analysis from Dr. Beatrice Villarroel, well known about her analysis of astronomic observation of potential UAP. So she will provide an analysis of space case. And after that, we'll have a paper presented by Professor Kevin Knut, well known also from University of Albany. And by the way, Professor Kevin Knut supervised the preparation of an article with a tremendous contribution of different associations concerning the work which has been achieved during decades on the research of UAPs. And Professor Knut will present a paper on review of measured speeds and acceleration of UAP and UFOs measured and also analyzed. Then Dr. Jacques Vallée, well known with Mr. Geoffrey Misterski, and with my contribution, worked on an article that has been proposed to an aerospace review well known in the USA. What about the Ainsville case? I won't detail that, but this is a very interesting detailed case. Why? Because it was part of the Condon Commission investigation. It happened in 1966. It was about a luminous sphere that was observed with a high energy apparent, and then later on, some more information happened. Some samples from trees that had been radiated were recovered, and some recent analysis were done. I'm not going to detail that more. Then we'll have a short presentation of the Valençol 1965 movie made by the filmmaker Dominique Fillol, because it was the anniversary of this event, which is taking place just the day before this webinar. And then we'll have two presentations on observation, one from Dr. Laura Dominé about the development of artificial intelligence model to apply to UAP characterization in order to use this data and help the extraction of information on UAPs. And from Mr. Raymond Piccoli, directeur du laboratoire de la foudre, on the observation of objects from Farfadet, a network, which is a network designed to collect data on transient luminous phenomena, but also possibly on UAPs. And then we'll come to a round table, which will be supervised by General Armament retired Pierre Bescon, well known also because he belonged to the Cometa group. and he will supervise together with me and with Baptiste Frescourt from Sentinel Center. So I'm done. I made the introduction on this webinar, and I hope you will enjoy listening and learning from these speakers with their excellent presentation. Thank you for your attention. The first session is about some UAP cases analysis. To start with, a presentation from Mr. Robert Powell. Mr. Robert Powell is part of the Scientific Coalition for UAP Studies, SCU, and is an SCU founding board member. The subject is about Stephenville lights. This is a comprehensive radar and witness report study regarding the events of UAP that were observed on January 8, 2008. This paper is presented and co-authored with Mr. Glenn Schultz. Then we'll have a second paper presented by Brigadier General retired from French Air Force, Mr. Jean-Marc André, together with contribution of Mr. Emmanuel Plichon and Mr. Philippe Chopin. The three of them are members of the Sigma 2 Technical Commission. And the subject is about the comparison of different UAP cases analysis, where they used radar data and data cross-referencing, for example, with visual data or infrared camera data. This case, without coming into details, are about the Cougar case, the Aquadia case, the Jersey case, and finally, the Stephenville lights case. After this presentation, we'll have a presentation from Professor Kevin Knut from SCU and chairing in physics, the chair in the university at Albany University, and is also chairing the UAPX Technical Society. And Professor Kevin Knut will present us a review of the measured speeds and accelerations of UAP and UFOs in different cases. Afterwards, we'll have a presentation from Dr. Jacques Vallée from Documatica Research, together with Mr. Geoffrey Meschersky from AAAF Sigma 2, and with my little contribution to the study. It was about the Haynesville case analysis in Louisiana. This case happened in 1966 and is about a ball of light, very intense, that was observed from a car at hundreds of yards, and some analysis of the power radiated and also of some chunk of wood that were in fact burned, and this is a very interesting subject. So we go on with Jean-Marc presentation with the support of Emmanuel and Philippe. Let's go.
Good afternoon, everybody. The study of UAP has long suffered from the lack of a measurable or verified information elements. The emergence of optical data collection in the visual infrared and the recording techniques, as well as radar detection, has been the revolution. Visual or optical observation cannot provide relevant information on distance, size, speed. Radar-type sensors can measure distances or speeds and compensate for this deficiency. The analysis of UAP has made significant progress with the use of these techniques in a data cross-referencing approach. The presentation first recalls the cases of the Chilean Cougar and the DHC-8 of Aguadilla. that have benefited from these advancements and for which interesting results have been achieved. Then it will address the cases of Jersey and Stephenville, where no image data is available. On the other hand, the radar data is abundant and of good quality. It shows how we had to adapt the analysis methods and to develop new data analysis techniques. This is the case of the Chilean Nave Koga. Will remind the story. It happened in November 11th, 2014. This helicopter is equipped with a Westcam optronic turret, and it has been carrying out a routine daytime flight. During this flight, the crew observes and films an object that intrigues them. The radar control agencies detect nothing that corresponds to what the crew describes. The Aguadilla case. A US Coast Guard DHC-8 is preparing to take off from the Aguadilla aerodrome for a routine mission when the control tower asks the crew to go and observe the northern sector where an intriguing radar contact has been observed. After takeoff, the DHC-8 makes a first part over the sea, but sees nothing, and during the start of the second round, the crew visually spots an orange light and then confirms an infrared contact on a Westcam control screen. The video images gave the impression of the fast flying object close to the ground. Here we can compare the data available for both cases. You can look at that. It's quite similar. And we could think that we could use the same method, and yet we had to develop processing method, adapt them due to the difference and peculiarities of the two cases. I will explain that during the following. In the Cougar case, we could reconstruct the trajectories of the detected flight from the data extracted from the screenshots. And we could perform an analysis of trajectories in confrontation with the geometric data extracted from the video. The comparison of the geometric parameters related to the Airbus Cougar configuration with the geometric data extracting from the video shows that the aircraft correspond closely to what the Cougar crew observed. I've forgotten to tell you that the Airbus is the aircraft which corresponds better to what the crew sees on the Westcam screen. The comparison of the geometric parameters is confirmed by the analysis of the Airbus Cougar configuration. We calculated the appearance of the engines viewed from the Cougar to compare it with which is shown in the infrared images of the video. The chosen point of the Airbus trajectory corresponds to the moment when a change in focus produces this particular infrared image. The superposition of the calculated point and the hotspots on the image confirms the identification of the Airbus IBE 6830. And now we pass on the Aguadilla case. In the Aguadilla case, which happened at night, the video only shows infrared images. With astonishing peculiarities, UAP image is occasionally disappearing, fading, or splitting. The UAP appears as single hotspots. The true shape cannot be determined as it requires sunlight to reflect on all surfaces. So we can say that there is one hotspot only. The dimension calculated is about 1.3 meters. Here you can see on this slide the red line. It is the trajectory of the DHC-8 according to the flight data embedded in the video. This trajectory is confirmed by our radar data. Yellow lines are the line of sight of the electronic system on the target. The laser system inside the Westcam turret is unable to hit the target, so laser measurements are taken on ground points. The green line is the continuation of these ground points. The analysis of the radar detections shows that no object has been radar detected on the lines of sight. So the bright object reported by the control cannot be the one pursued by the DHC-8. Based on the line of sight, we perform simulations of trajectories by assuming a constant vertical speed. The blue line represents the result of the simulation, and the graph on the right shows the speed of the simulated UAP. You can also see the DHC-8 trajectory and the ground track of the line of sight. And you see also the coastline. This is the active graph. On the left side of the graph, you have two spin buttons that allows me to change the initial UAP altitude and the UAP vertical speed. And look at that. When I change, we have the change of the profile of the trajectory. And which is very interesting is to look at the right. Here you can follow the variation of the speed and check the consistency of that. Okay, you see it's very amazing, and you have different trajectories possible, and this is exactly that we have studied. This slide shows the differences between infrared signatures and drones, jets, aircraft, and also lanterns. Finally, we favored two possible solutions without being able to affirm certainty, and the causes of the disappearance, fading, and splitting remain undetermined. So that could be the most preferred hypothesis are the fast mini or micro UAV or the tail lantern. We see that by using radar and optical data, we have been able to solve the Cougar case and made good progress on the Aguadilla case, but without being able to reach a conclusion. In the two following cases, that of Jersey and that of Stephenville, no optronic data is available. We only have radar data to compare with the visual testimonies. On the 3rd of April 2024, a Trislander, which is a 3-engine piston-powered aircraft, is cruising southward over the sea bound to the Channel Islands. 3 o'clock p.m., it comes from Southampton with 9 passengers. The aircraft flies steady at 4,000 feet and prepares to descend for landing at Alderney, one of the islands. At one point, the pilot notices a bright light straight ahead in the axis of the aircraft. The pilot contacts the air traffic controller of the Jersey control zone, and until he loses the sight of the UAP, he exchanges information with him to try to identify the phenomenon. Better still, the controller involves other crews in flight to participate in this kind of hunting. What is remarkable, that is the participation of several actors in real time for research and analysis. Unfortunately, they were not able to provide any answers. And thanks to the very precise timings of radio exchanges and radar detections, it has been possible to establish clear and accurate pictures that facilitated the search for candidate tracks. We couldn't find any identified track matching with the testimonies. Identified means secondary detection with an indication of an IFF code. Regarding the primary detection, we noticed about 15 interesting alignments of plots, some of them showing very odd properties. For example, track P1 that we can see on the slide, this track shows periodic detection losses. We are still working on the reason for the phenomenon, which could be in connection with the UAP. We called it the frog lips track. Another phenomenon is the very straight alignment, like which one we see circled in red. These alignments are due to the extracting system of the radar. The distances of the radar jump from discrete values to another discrete value. It's about 120 meters. And then, as a result, the plots are aligned. We could think that they represent the same object. Was not true. 5 of these tracks could match the reports given by the pilot regarding the position, but we couldn't establish a link with the flight progression. You can see here the geometric configuration at the right, and then the representation of the direction in which the pilot can see the tracks in the cockpit of the trace lander. This is in the upper part of the slides. And you have indications of each of the 5 tracks which have been chosen. Now we have a look on the Stephenville case. On January 8, 2008, between 6 p.m. and 9 p.m., 13 individuals reported seeing bright flying objects, sometimes accompanied by the sound of jet aircraft. And you can see that the witnesses are spread over a fairly large area southwest of Dallas-Fort Worth, Texas. What we could get? Witnesses are in separated and distant places with no connection. The observations are not concordant. The lights, the number of lights, number of objects, noise or no noise. The timings are very approximate. The investigation area is large. The duration of the observation slot is very large also, and we have a big, large complexity of the air situation. So during the 4 hours of recording, we had more than 1,000 identified movements. It's much more interesting to see. So we had to explore some directions to try to find some explanations because it's very difficult to compare all the tracks with all the 13 testimonies. This is the area. We can see here the airfields, Fort Worth, Dallas-Fort Worth International, DFW, other airfields in Dallas, Addison, and Love Field. You have Stephenville and Dublin. What we can say about these civil airfields, there is a very important activity. we had 54 takeoffs during the record period and 65 landings. But we have also 3 Air Force bases. Carswell, CAFB on the right part of the slide, but also Dyess Air Force Base and Shepard Air Force Base in the north. Alors, what are doing these air base? Carswell operates the F-16 of the fighter squadron for the reserve, and they fly mostly in the military operating area, the MOA of Brownwood that you see on the bottom of the slide. And they also operate on gunnery, air-to-ground gunnery and bombing range, Falcon range, on the top of the slide, north of a Shepard Air Force Base. This is very important because we could analyze the flights in function of these elements. What we must know also is that Dyess Air Force Base operates 2 types of aircraft. First, the bombers, the B-1B Lancer. About 30 B-1B are stationed on this airbase. Shepard Air Force Base hosts a special organism. It's next to Wichita Falls. The base hosts the 18th Flying Training Wing, with activities centered on the Euro-NATO Joint Jet Pilot Training. The aircraft used as the T-38C Talon and the T-6A Texan II, and they could operate in the area. What else about this slide? Okay, the blue points, the blue dots are the places of the different radars, civilian radars. The FTW is the radar for Fort Worth, and okay, one is missing here. As it's impossible to analyze all the flights, we could filter the flights flying in over the zone where the UAP has been observed. And we analyzed these flights, the profile of these flights, to check if they could be the origin or the cause of the UAP. No aircraft. They are all identified aircraft with an IFF, and we can check the altitude, and no aircraft of this aircraft was an altitude lower than 15,000 feet when it was in the Stephenville area. And at more than 15,000 feet, it's very hard to imagine that it could have been the origin of the observed light phenomena. One track that you can see, it's IFF 4622, has been lost close to Stephenville. It was lost because the descent below radar horizon, certainly an helicopter. We saw it took off from Dallas Hospital. And it's not alone to have been lost. There is a large number of aircraft, identified aircraft, which have been lost for the same reason, passing below the horizon of the radar. And the problem is that it's impossible to know what happened, what they could do after the Columbia contact was lost. Another interesting track is the track of the AWACS, an AWACS that you can see is flying regular patterns, high altitude. It's on a brown, you can see it in brown dots. And regarding the F-16 trajectories, the F-16 from CAFV, Carswell, we have noted nothing unusual in the trajectories of the identified aircraft, nor those of the crew members without IFF that we have reconstructed. So we are speaking about the radar horizon. Here is the detection profile of the Fort Worth radar in the direction of the UAP observation area. All the dots are actually detected secondary plots. The black points are the secondary double with primary points. The brown one has secondary without primary. The blue line is the calculated horizon due to the rotundity of Earth. And we had the profile of the ground with the place of the Stephenville, Dublin, Comanche. And we can see that in this region, a larger part of the space is unexplored by the radars. So it can happen a lot of things that we cannot know at all. We conducted research on primary detections by identifying alignments of plots. Some are clearly identifiable. For example, this track, starting from Dublin and going east to southeast in the direction of Prairie Chapel Ranch, the Bush Ranch. I take the opportunity to show you at the bottom left of the slide the plots of the F-16 evolving in Brownwood and MOA. These are not skulking aircraft at the F-16 flights, and it's amazing that they continue not to skulk, even though they are no longer in a close formation. Okay, when you see at the map, you see that it's much complicated to analyze all that. So we have developed some improvements to support the search of primary plot tracks. 29. The first improvement relies on the STK tool. This tool allows dynamic 3D simulations of detected flying objects with visualization of radar hits during the flight. The analysis process has been developed by Philippe Chopin. A second improvement consists in developing algorithms for searching for spatial and temporal coherence of sequences of plots. The process takes into account the geometric aspects of visual testimonies. It has been developed by Emmanuel Plichon, and this process proves to be perfectly suited when you have to take into account the UAP observation testimonies. All the testimonies have been analyzed this way, but unfortunately, without any conclusive result. So, we have also imagined a completely different approach of the study. It consists in exploring the distribution of IFF codes of the identified flights in order to characterize the types of mission of flights. The idea is to highlight scenarios that open up a hypothesis for explaining UAP. This map shows the flights identified by an IFF whose first digit is 5. There are a large number of civilian as military flights. You can see the F-16 combat training trajectories on the left bottom of the slide. we can see all the aircraft, civilian aircraft arriving or departing the Dallas-Fort Worth airfields. We can see the activity on the gunnery and bombing range, Falcon Range, and some activity north of Falcon Range on the top of the slide. I think they are connected to the Falcon Range activity. What else? You notice on the left side, part of the slide, close to DICE, a number important of trajectories and probably departing aircraft, arriving aircraft. Okay, and you have also some other trajectories which merit to be investigated. The study of this approach is still ongoing. We have not found anything interesting for the moment. Conclusion. Nothing significant could be discerned regarding the UAPs of Stephenville. It has been shown that many aircraft have been able to carry out part of their flight in the UAP observation area at low altitude where radar detection is deficient. They can be civilian or military aircraft. We observe the coincidence of several military flights coming from several bases at the fall of the night with the presence of an AWACS. The hypothesis of a military exercise cannot be ruled out. We could examine 4 cases of UAP observation, all of them well documented in radar detection data. In 2 of these cases, we had video recordings with measurements information. The investigation could be concluded with the statement of a precise solution or propose specific solution hypothesis. In the other 2 cases, we were able to analyze the radar recording data and draw interesting insights from it. But the matching with the visual testimonies was completely unsuccessful. And finally, as a general conclusion, we can say that each case requires the development of its own methodological approach. Thank you for your attention.
Okay, so now we are coming to the next presentation by Professor Kevin Knut. Hi, Kevin. It's very happy to see you.
Hello, very happy to see you too. Thank you for having me.
Okay, so, you are one of the 2 persons to provide a presentation, a live presentation. So, the floor is yours.
All right. Hello, everybody. I'm going to basically give a review of measured speeds and accelerations of UAP. All right, I'm going to start back with Hermann Oberth, who was the German father of modern rocketry. He was mentor to Wernher von Braun. And you can see him in this photo on the upper right. This is the grumpy gentleman down in the foreground. And in 1954, he gave a lecture on flying saucers. And in this lecture, he said that their speed is sometimes very high. 19 kilometers per second has been measured with radar, basically. And he notes that if there would only be 3 or 4 measurements, I would not rely upon them, and I would wait for further measurements, but there is existing more than 50 such measurements. So he had access to over 50 radar measurements, radar recordings of UAP speeds, and noted that speeds up to 19 kilometers a second have been recorded. That is 68,000 kilometers per hour, which is about 42,000 miles per hour. So let's get this straight. This is a really important point. It's clear from this alone that it has been known for over 70 years that UAPs travel at speeds of 68,000 kilometers an hour, about 40,000 miles an hour. As comparison, that is about the speed of the New Horizons probe, which visited Pluto back in 2015. The International Space Station travels at about 8 kilometers a second. So UAPs have been measured traveling twice that fast, twice as fast as low Earth orbital speed. These are very important points that anybody studying ufology should know at this point. Anybody interested in UAPs should know. At this speed, a UAP can go from New York City to Paris in 5 minutes. That's faster than taking a taxi from the Arc de Triomphe to the Tour Eiffel, or faster than going across Midtown Manhattan the short way. And so this puts quotations from officials in a different context. So Herman Oberth wrote that it is his thesis that flying saucers are real and that they are spaceships from another solar system. He said, I think that they're possibly manned by intelligent observers who are members of a race that may have been investigating Earth for centuries. I think that they possibly have been sent out to conduct systematic long-range investigations, first of men, animals, vegetation, and more recently of atomic centers, armaments, and centers of armament production. That latter statement has been borne out by the intentions study that was recently conducted by SCU. We have here the quote from Vice Admiral Roscoe Hillenkoetter, the first director of the CIA. Behind the scenes, high-ranking Air Force officers are soberly concerned about UFOs, but through official secrecy and ridicule, many citizens are led to believe the unknown flying objects are nonsense. Tied the facts the Air Force has silenced its personnel. They're still silenced. When Congress asked for reports on UAPs, the Air Force did not reply. This is a problem. They have known for 70 years that these things fly at spacecraft speeds. This is not a surprise. It's clear that these are non-human craft. There's really no beating around the bush about this. Colonel Joseph Bryan said the UFOs are interplanetary devices systematically observing the Earth. And the same types of statements have come from the Soviet Union and from Great Britain. This has been known for decades. None of this is new. In fact, it's been known much longer. Charles Fort from Albany, New York, where I am right now, known as the first ufologist, wrote on September 5th, 1926, 99 years ago, in the New York Times that it is not the conventional or respectable thing upon this earth to believe in visitors from other worlds. Most of us could watch them a week and declare that they were something else, and likely enough make things disagreeable for anyone who thought otherwise. That's 100 years ago. We're all just playing catch up at this point. All right, so based on the observations, what are these capabilities? So I'm going to review some of the cases that we've looked at. The first is the Bethune encounter. There's a nice interview with Graham Bethune from the U.S. Navy back in 1951. They had been sent to Iceland to check out a UFO that was near Reykjavik. And on the way back off the coast of Newfoundland, they encountered a large disk that apparently was underwater originally. They saw the lights underwater about 6 miles ahead of the craft, or their plane. The UFO, they estimated later to be about the 300-foot diameter, about 100 meters in diameter. So they were flying at about 125 knots at an altitude of about 10,000 feet. And 6 miles ahead, they saw this object come out of the water and fly up to their plane in less than a second. So you can estimate the acceleration. You can estimate a minimum acceleration, assuming that it accelerates halfway and then decelerates the other half to arrive at the plane. So we're going to put numbers on these. I'm going to put on about 10%. I'm going to put on some reasonable uncertainties here. And And basically to estimate what its acceleration was, we will do a Markov chain Monte Carlo sampling of these numbers, basically try many different values and then estimate. So these are the various times that it could have been. They said less than a second. Oh, they might have been mistaken somewhat. Some might have been 2 seconds, might have been 3 seconds, less probable for that. The altitude, they were flying around or close to 10,000 feet. So we've actually lowballed it a little bit, which will give us a more conservative estimate for the acceleration. We're again trying to be conservative here. And sampling the angles that they measured the object at gives the distance of, on average, about 6 miles. Could it have been, if you're off by the angular measurement, it's more probable that it's further away than closer. And that's what this distribution shows you. So now if you estimate the minimum acceleration, you find that the acceleration was on the order of about 1700 g, 1,700 times the acceleration of gravity, which is incredibly high. We'll look at another case. This case was studied by Claude Poher, and this is the Minot Air Force Base case in 1968, where you had a B-52 bomber was on approach and was alerted to watch for bright glowing orange UFOs. And this was actually picked up on radar. The object was egg-shaped. There's a drawing of it in the upper right here. and it was glowing like molten lava is how the pilots described it. The acceleration, basically the object closed a 2-mile distance very rapidly, and Claude Poher estimated the acceleration to be about 200 Gs with a top speed of about 15,000 kilometers per hour or 9,000 miles per hour. So again, these things are clearly very fast and clearly not human technology and not natural. The most shocking case is probably this one, and this is probably the best recorded. This is the Japanese airline case from JAL 1628 from 1986. In November, was flying across Alaska and encountered several UFOs. A large one, which was estimated to be about twice the size of an aircraft carrier. Here's a drawing of the object. He described it as a walnut-shaped. This little thing down here in the lower right, just below the object, is the size of a 747. So this thing was huge. You have to ask yourself, how wrong would the pilot have to be to think that it's huge? If he's off by 20%, the thing's still huge. This is pretty clear. Dr. Daniel Kumbe analyzed the 11 jumps that were made by the UFO across the path of the 747 during the time that it was recorded. This was published in his book Anomaly. 3 of these jumps exhibited accelerations exceeding 9,000 Gs. The fastest one was down here in the lowest right, 10,786 Gs, with some uncertainty, of course, of plus or minus 815 Gs. So that gives you a top speed of about 432 kilometers per hour, which is about 269 miles an hour. To give you an idea of what you can do at that speed, you can reach the moon in 53 minutes. We could leave now and get to the moon for dinner and be back for bedtime easily in a craft like this. And this craft is the size of 2 aircraft carriers. This is pretty shocking. That radar data was collected from John Callahan, who was the FAA Chief of Accidents Investigations. It was taken from him by President Reagan's scientific team, and he fortunately saved copies that he kept under his desk for another 20 years until he retired and took them with him. And that's how we have access to this data. So thank you, Mr. Callahan. The other case I'm going to talk about briefly, but we know very well, and one of the most modern cases is the U.S. Navy case from the USS Nimitz encounter in Southern California in November of 2004. The USS Princeton, which is part of the Carrier Strike Group 11, had been tracking mysterious aircraft intermittently for over 2 weeks in November of 2004 using the AN Spy 1B passive radar. According to Senior Chief Kevin Day, who was the radar operator, these things would appear on his radar at about 80,000 feet. That was the ceiling of his radar. They did have radar that went higher. Those radar operators have not come forward, although Kevin Day has intimated that they were detecting them dropping in out of orbit, but that's not been verified. These objects would appear at 80,000 feet and then drop to about 28,000 feet just south of Catalina Island off the coast of Laguna Beach, where our UAPX team conducted our first survey several years ago. A paper describing that has just been published this last month. Its first author is Matthew Shadagas, and it's been published in the Progress in Aerospace Sciences. But Kevin Day had noted that these objects would periodically drop from about 28,000 feet to sea level in 0.78 seconds, and that allows us to estimate speeds and accelerations again. So we've got a vertical drop from 28,000 feet to sea level. I'm putting on about 10% uncertainty here. And we can then work out these equations, which are pretty straightforward. A high school student could do this, a high school physics student could do this, and have done it. There was a school in Georgia that actually used the paper that I wrote with Robert Powell and Pietro Reale on these speeds and accelerations. They actually used that as a homework assignment. So if high school students can do these calculations, so can science popularizers who say that this is nonsense. They should be doing calculations first before they open their mouths. So again, we sampled from Gaussian distributions here to arrive at a distribution of accelerations. You can see the most probable acceleration here given by the red line is about 54,000 Gs. I'm sorry, 5,400 Gs, 5,400 Gs. And the mean acceleration is slightly higher because it's a skewed distribution at almost 6,000 Gs. Yes, there's a great deal of uncertainty here, and that's fine. But all of the probability mass is basically above 2,000 Gs. So we can be very certain that these things are accelerating at incredibly high rates. The energy, if you assume that the tic-tac shaped objects that they were tracking are about the same size as an F-18, if you take 1/10 of that mass, if you're conservative, so the mass of an F-18 is about 10,000 kilograms. So if we take the mass of the tic-tac to be 10% of that, just 1,000 kilograms, with this acceleration, you can estimate the power required to perform the maneuver, and the maximum power required is 1,100 gigawatts. There's something really off here. The nuclear power production of the United States, the entire United States, is only 98 gigawatts. So this little tic-tac is carrying a whole lot of energy. We all know, especially those of you in engineering know, that no machine is 100% efficient. So even if you have a 1% inefficiency, if it's 99% efficiency, you've got a 1% inefficiency, you're looking at waste heat of 10 gigawatts. It's a nuclear power plant worth of waste heat. Things just aren't adding up properly. This is a big clue as to what's going on. So we now are aware that it's been known for over 70 years that UAP move at spacecraft speeds. we can then ask, are these accelerations consistent with the hypothesis that these are extraterrestrial? I mean, could they be interstellar craft, some of them? Are they interstellar capable? So here's a summary of the cases I've looked at. We've got accelerations ranging from 200 Gs in the Minot Air Force Base case, all the way up to about 10,000 Gs for that giant UAP that followed the Japanese airline across Alaska. Just to be clear, an acceleration of 25 G would kill most living things. Humans aren't going to survive more than 10 G for any period of time. Fighter jets themselves can't withstand more than about 13.5 Gs before their wings get ripped off. So these accelerations are unreasonable and clearly non-human. So we can use the relativistic rocket equations to see what happens if these things were able to maintain that acceleration for any period of time in space. And to give you some example, if you look at these objects, so these craft would be moving at relativistic speeds rather quickly. I don't have the plot up here that shows how fast it'll be going at us after a certain period of time, given a number of Gs, but at 1,000 G acceleration, you would reach 90% the speed of light in 17 hours. So this puts you into the relativistic realm pretty quickly. That means that they're going to be experiencing time dilation, and that means that getting to Alpha Centauri, a ship that accelerates at only 100 G, which is less than the case examined by Claude Poher at Minot Air Force Base, you can get to Alpha Centauri in a month. Of course, for everybody on Earth or Alpha Centauri, this is going to take 4 years. But for the people on the ship, it'll only take a month because of time dilation. You can get to Vega, which is a little more than about 25 light years from here. At a 200 G acceleration, you can still get there in a month. If you're traveling at 1,000 Gs or higher to the 10,000 G acceleration, like the aircraft carrier-sized ships, these are all day trips to the nearest stars. It's a day trip. So not only are these craft accelerations consistent with being interstellar capable, they're interstellar excellent. It's a whole different ball game. And we wrote that in me and Peter Reali and Robert Powell put that in our paper that was published in 2019, where we estimate the speeds and accelerations of these craft. We noted that not only are these possibly interstellar craft, but they're excellent interstellar craft. So there has been published papers suggesting that these are non-human craft. How far could you go? This is assuming that you are accelerating at 100 G, which is on the low end of observed accelerations, and you accelerate halfway and then decelerate the other half. You can get this distance away from the sun in 90 days. 100 days, you're getting close to the center of the galaxy. 110 days, you can make it to the other side of the galaxy. So at 100 G acceleration, less than a year to get from one side of the galaxy to the other. All right, so thank you very much.
Yeah, that's flown from one side of the galaxy to the other. A lot of strange stuff.
All right, are there any questions?
Well, maybe we can wait for the debate, but for sure, I have in mind, and I leave you time just to think of it. It's completely amazing to see the measurements, or at least the detection in case of the Nimitz case, detection by SPY-1. And one of my question is, well, they conducted detection and tracking of the object changing of altitude or they saw one radar track just disappearing from its level at 80,000 feet, and then found a new one at the level of sea. Because I'm very impressed by the capacity of tracking an object which is submitted to such huge acceleration. You know that for aircraft and so on, of course, the design of military sensor is done to be able to detect and track the objects, whatever are the maneuvers or the missiles. But here, we are really looking at huge acceleration, and I'm just thinking of the continuity of the image picture, of the radar picture, if you wish. If you had any insight on that regarding these objects.
Right. Well, when it comes to tracking these things with radar, my understanding is that the tracking isn't necessarily continuous in all cases. I know that in the Japanese airline case, the radar was sweeping back and forth with a 10 or 12-second delay. And so the object would be in one location with one sweep and another location with the second sweep. And in that case, you can estimate the minimum acceleration it would take to get there. And I think that's probably what's going on with the Nimitz case as well. Perhaps not sweeping, but I don't think that they had continuous tracks measuring the acceleration. It was at 28,000 feet at one point in time, and then 0.78 seconds later at 0 feet. And that's basically how Kevin Day described the object as it left David Fravor. When David Fravor tried to approach it, the object shot across his nose and accelerated off into the distance and went to their cap point. Kevin Day did not track it to the cap point. It basically disappeared from where it was with David Fravor and then appeared where it was at the cap point. And he's assuming that was the same craft. So I don't think that these accelerations are easily tracked. These speeds are very high.
Okay, thank you. I propose that we continue the presentation, and anyway, we'll come back to discussion and exchange of views during the round table. But thanks a lot for your overview of acceleration estimates for various cases of UAPs, and a long time, you know, because starting a long time ago, nearly 1 century, and then coming to more recent events. Thank you.
Okay.
This presentation concerns an exceptional observation of an identified phenomena that took place in the southeast part of the United States at the end of 1966, in December of 1966. And it came to my attention as I was working with Professor Hynek in Chicago early in 1967. So we have gone over this presentation and this case in detail with a French, American, and English team. My colleagues are Mr. Luc Dini and Mr. Jeff Michersky, and also Dr. Nicolas Nias in London. The observation was reported by the witnesses to the Air Force, to the United States Air Force Project Blue Book, and I was at the time compiling statistics on behalf of the Air Force with a small contract. I was preparing my doctorate at Northwestern and finishing that work. And I had this, the Air Force had suggested that I go over the statistics of Project Blue Book. And I found this case and thought it would be interesting to submit it to the Condon Committee at the University of Colorado. In 1968, the Condon Committee began its work and started to do research in the field. And that was the opportunity for us to present the case to them as a new and interesting physical physical data case. And then we have re-examined the case because, as you will see, there are significant physical traces that can be analyzed and that we continue to analyze. The case centers on an observation that was made late in 1966, and you will see in a minute why it's very important still today, many years later. Dr. Hynek was at the time a consultant to the Air Force. Dr. Hynek and I were the first scientists who had briefed the Condon Committee at the University of Colorado at the time, and we submitted the case to Dr. Condon. The case is exceptional in spite of all the years that have passed, because of the extremely high energy that could be computed associated with the object. And this is a very rare example in the whole history of UFOs. Many people say it was very bright, or it vanished and it reappeared, and the light was this way and that way. There are very few very well observed lights in terms of their intensity, their changes in time, and giving us a way to actually compute the energy. The energy that we computed with the witnesses and with the Condon Committee was in the range of a nuclear power plant in an object that was just a few meters in diameter, that had landed in a clearing in a forest. And that is why the case is important, and that is why our report was recently published in the #1 aerospace review in the world. The observation took place on the evening of December 30th, 1966, on an isolated highway that was traversing a forest near Haynesville in Louisiana. The witness happened to be a professor of atomic physics, a young man in his mid-30s named Dr. Louis Galloway, and he reported the case to Project Blue Book of the United States Air Force. That's where I found it, because at the time I had a contract with the Air Force to redo all the statistics of Project Blue Book. And then I thought that the case was exceptional, and I suggested to Dr. Hynek that we should bring it to the attention of Professor Condon, himself a brilliant atomic physicist in the United States. Edward Condon had been with Dr. Oppenheimer at the Project Manhattan at the time of the first atomic bomb. So we put Dr. Condon in touch with the witness, and that's where the analysis of the case began. The case centers on a very well-defined object at ground level, and it led to estimates of energy initially between 500 and 1,400 megawatts, which is in the range of a small modern nuclear power plant. Since then, as you will see, more sophisticated analyses have been done by our team, both in France and in the United States, and that's what we are reporting. The case was examined by Dr. Condon and by the Air Force, and is carried as unidentified in the final report from Professor Condon and the team in Colorado to the American Academy of Sciences. So this is not us saying that the case is unidentified. It's the analysis done by the Air Force and the University of Colorado project as reported to the Academy in the United States. And we are building on that initial analysis to try to refine it with new data that has been found in the meantime. After the Academy report, significant work was continued at the site by the main witness because they had not found the exact spot in the forest where the light originated. And he went back with one of his colleagues, also a professor of physics, and they located the clearing where the object had been seen. At the time, Dr. Galloway was driving home with his wife and 2 kids. It was raining. It was at night. He was going through the forest, and he saw that very bright light over a kilometer away from him. As you will see, we were able to recover, once the clearing had been found, some of the wood from some trees that had been illuminated by the light of the object and burned was saved. And we have the samples of the wood. So our team has reanalyzed and continues to analyze the energy characteristics that have impacted the wood of the trees. So the burn analysis data that we will present was obtained at the laboratories of the French Atomic Energy Commission in Saclay in France. And we present our results with the understanding that this is just the beginning. And we would like to enlist the help of other specialists in atomic physics to continue the discussion and to continue the study. My presentation will be in 5 sections. First, I'll talk about the basic data, then the case analysis as it was presented in the Condon Committee report to the Academy, then the detailed site analysis that the witnesses were able to do afterwards, the study of the physical conditions at the site, and then the initial energy calculations that were made by both teams over the years. And then this will be continued by the work that has been done in France since then to refine the measures of the energy. So the observation was made on the 30th of December 1966, about 8:30 at night. We know all the conditions, we know exactly where it is, we know the time, and we know the weather from 2 different weather stations within the location. The location is 1,200 yards west of Highway 79, 3.6 miles north of Haynesville in Louisiana. So that the sighting itself was actually in Arkansas, in the next state north of Louisiana, about 1 mile north of the border. The main witness was Dr. Louis Galloway, 31-year-old. Mrs. Galloway was 28, and 2 children, ages 5 and 7. At the time, Dr. Galloway is a professor of physics at Centenary College in Shreveport, Louisiana. The area is about 30 miles northwest of Shreveport and 100 miles south-southwest of Little Rock. So we want to be very precise about exactly the area and the conditions at the time. Dr. Galloway sent a standard witness report to Project Blue Book at Wright-Patterson Air Force Base, which I was reviewing at the time under contract with the Air Force, and I selected the case to show it to Dr. Hynek and then to Major Hector Quintanilla, who was in charge of Project Blue Book at the time. All of us thought it was important to follow up because of the credibility of the witness and the detail of the observations. So we called, Dr. Hynek and I called Dr. Condon in Colorado to tell him about the case, and we put him in touch with the main witness. Dr. Condon agreed, and his group of about 15 physicists and scientists in Boulder, in Colorado, undertook extensive follow-up studies. Two of his associates with doctorates in science went to the site and took measurements and interviewed the witness and started aerial surveys at night with aircraft that took infrared photographs. And we have those photographs. Unfortunately, at the time, this is a very dense, very large forest, and they were not able to pinpoint the actual site, which we have done now, we have done later. The Condon report to the Academy of Sciences summarizes the case as follows. A family had reported observing a pulsating light which changed from a red-orange glow to a white brilliance, which washed out their car headlights and illuminated the woods on both sides of the highway. The driver had to shield his eyes to see the highway. About 0.6 miles farther down the highway, the driver reportedly stopped the car and from outside the automobile watched the light which had returned to the original glow. The light was still there when he stopped observing and left the area about 5 minutes later. Although our investigating team made an aerial survey of the area and watched the reappearance of the phenomenon, and the principal witness continued to search the area, no revealing new information was discovered, and the source remained unidentified. And the case is carried in the Air Force files as unidentified and reported as unidentified to the Academy. Actually, Dr. Galloway and Dr. Condon shared expertise in nuclear physics. Dr. Condon had been at the Trinity nuclear explosion in 1945. So they collaborated closely in researching the case. The media was not aware of any of that. There was no interference from either amateur groups or media. However, the Air Force became actually very interested in the case again and contributed to the study. The Condon study consists of major conclusions in a few pages, which is what people have read. So people think the Condon study was completely negative. The study was not negative. The study said there is not enough information now about the cases that we could not identify to justify a major investment by the United States in the UFO phenomenon. We may disagree with the conclusion. I disagree with the conclusion. But the appendix to the study, which was published with it, contained 1/3 of all the cases that the committee had looked at were, in fact, unidentified. And in that section, in the appendix, there are 4 pages about this case. And that mentions the infrared photographs and the complete weather data. The Air Force continued to collaborate with the investigation, and we have a letter from February 1967 from a Major Donald Ryan, who was investigating officer for the Air Force, who wrote to the Foreign Technology Division at Wright-Patterson Air Force Base in support of the conclusion that the case was unidentified. He had done his own calculations of the energy, and through triangulating as best he could the source of the light, he computed the distance from the road to between 0.7 to 1.2 miles, which would be about 2 kilometers. And using this distance, he computed the power of the light source and he found between 400 and 1,200 megawatts, again, which is in the range that we're talking about. And that's where the importance of the case is still present today. The Air Force officer returned to the site in an attempt to find anything that might explain things at the site. And he concluded, Major Ryan concluded with his, quote, most strong recommendation that the Air Force contact other witnesses and cooperate in every way in attempting to find a solution to the unexplained light. Following my phone call with Professor Condon, the witness wrote to Dr. Dave Sanders, who is also a well-known colleague of ours at the time at the University of Colorado, to report the results of the aerial photography. And he had gone back on foot to study the site. Dr. Galloway had also searched for other witnesses in the area. And here again, this is typical of many cases where we have one witness and one site. If you do the investigation, you find there were other witnesses, and he found two other families in the area that had seen a similar object in the day before or a few days after his own observation, with an enormous amount of light that corroborated his sighting, but those had never been reported. And that is the data from which we resumed the investigation. Professor Galloway went back to the site after everything had been published with a colleague, another professor of physics, Professor John Williams, and they found the actual clearing where the object had been. It's a small clearing. The trees that were exposed are trees in a forest which is an industrial forest, which is harvested periodically to use the wood in construction and in a number of other industrial markets in the United States. So having found the site, they were able to draw a map, which we also have, a map of the area with the actual distances from which we can refine the measurement of the energy. The area contains trees. We know what types of trees. Contains underbrush and other items, but there was no train goes through the area. There was no other traffic and no explanation for the light in the clearing. The actual site is a clearing about 30 feet, about 6 meters, in about 10 meters in diameter. And the bark of the trees around the periphery was turned black by the radiation from the object. These are the typical trees that are grown in the area. Those are pine trees. There are 5 major types of pine trees. And again, this is an industrial forest where the trees are carefully harvested and replanted section by section over the years. We have the bark from the trees, bark from the back of the tree that was not affected by the radiation, and the part of the tree that was burned by the radiation. However, this is not a burn. This is not a high temperature that has blackened the wood. It's actually radiation. And with my colleagues, we've looked into what type of radiation it could be, and we continue to do that. We have complete weather records from, as I mentioned, from 2 different sites, commercial sites, and also the pilots from Barksdale Air Force Base flew a number of night missions with infrared photographs. And again, we have all the data about the weather, and we have the infrared photographs from the pilots. So again, this is a case where we have worked with the witnesses over the years to gather all the data that a true scientific study would demand. There is nothing of a vague Mrs. So-and-so or Professor so-and-so thinks that he saw a light in the forest. That is not the case. We have the precise site and we have the precise data at the time. So we now address the nature and intensity of the energy. The energy is the important thing. What kind of energy is likely to have been present at the site and to create this effect? There are a number of high energy events reported in the files of the different organizations in France, in England, in the United States, in Russia, that study the phenomenon. But there are very, very few cases where the energy was actually measured or calculated, and that there are only 2 or 3 cases that I know of from compiling those databases, as you know, that come in the range of what we have here. This type of energy, of course, can create injuries to humans, and Professor Galloway was very much aware of that. Professor Galloway did something that is exceptional at the site. He wanted to know the energy of the light in front of him. He knew the energy of his headlights. So he looked for the point where his headlights, close to the car, were washing out, were equal to the light that came from the object that was more than 1 kilometer or 1.5 kilometers away from him. Knowing this, he had a very simple equation, simple for a professor of physics at the time. And I'm amazed that he actually did the calculation mentally of the equivalence between the light in the forest and the light of his headlight. And that's when he realized that he was in a very dangerous situation. At the time, assuming that the distance was 2,400 feet, the light would have been, the energy would have been 900 megawatts. And if we take the second location, which is closer, of 1,800 feet, the light would have been 500 megawatts. And this went on in the discussion between Professor Condon and Professor Galloway. So this is in the range of, actually, of a nuclear power plant. The calculations are stunning. They are unique in the history of the UFO phenomenon as observed by scientists in contemporary science. We plan to continue to study the case and to redo the calculations based on the analysis of the wood. We have samples of the wood, both the wood that was burned and the intact wood from the other side of the tree that we have preserved, that I have preserved over the years, so that they can now be reinvestigated. This concludes my part of the presentation. This was the status of the case when we resumed the study, and my colleagues will tell you what we're finding and why we think this is an important case for future aerospace research. Thank you.
Dear all, I'm Luc Dini, chairman of EEF Sigma 2 Commission on UAP, and I'm going to deliver a few information as a complement to the presentation from Dr. Jacques Vallée and Mr. Geoffrey Mieszczerski on a famous case which happened in 1965, the so-called Hinesville case. So what you saw before was about the effect of a ball of light, a very powerful ball of light that you can see on the screen on the right part. And this ball of light was illuminating the road just in front of a car. This car was driven by Professor Galloway. He was very surprised by the intensity of light, so he stopped the car. And the story is about the estimation of the power radiated by this ball of light. A first computation was made by Dr. Galloway when he considered that the power of the headlights of the car, about 150 watt, was radiated around, scattered, if you wish, in the surrounding of the car. He made the math, used some equation, which is here on the left, and this equation is explaining that the intensity of this light, the yellow bubble, was the ratio of the power divided by the square power of the range between the car and in the area where the light is radiated. This computation gave some astonishing results because the power radiated by this ball of light, which was in fact superposed to the light radiated by the car, gave a result very surprising with a power between 600 megawatts and 800, if I remember. It was very, very, very high power that we can compare to a nuclear plant. However, we decided to revisit this computation, and we took a second hypothesis, if you wish. In this case, the entire power of the car is directed on the soil, on the ground, on the road, just in front of the car. So in this case, the equation is slightly different. Here, the intensity radiated is a ratio between the power and the square power of the range. There was another term, part of the equation, 4p, p being the Pythagorean number, and it means that the intensity is nearly, around 10 times higher than previously. So the conclusion of this computation, which in our mind seemed more realistic, is that given the directivity of the light generated by the car headlights, we come to an estimate of the ball light radiated power more than 10 times higher. So 10 times the power of a small nuclear power plant. Thank you.
Hello everyone, I'm Jeffrey from the Sigma 2 Commission, and I'm going to present you the result of the gamma ray spectroscopy of a bark sample. So, as it was said before by Jacques and Luc, the UAP event occurred in the middle of a clearing in 1966. The UAP was in the middle of the clearing, and it was very bright and shining. The witnesses, when they came back a few days later on the spot, they found trees from the edge of the clearing that they were completely blackened. And what is interesting here is that these trees, only the exposed faces of pines were affected. There seems to be irradiated by the UAP. So Jacques sampled one of the tree, and he took two samples, one from the exposed face, which is the sample A here in this case, and another sample on the other side of the tree, which is sample B. This is the actual sample, and as you can see, the sample A is black and not the sample B. Also, Dr. Galloway, when he came back on the spot, he performed contamination measurements directly on the blackened trees, but he found no radioactivity traces. What is interesting here is that when he came with a portable device, Dr. Galloway, he put it directly on the tree, but for sure he didn't stay hours to measure contamination. Okay, he had to do it few seconds, maybe 1 minute max, but which is very too short in a low level contamination condition. So it doesn't mean if he didn't find any radioactivity traces, it doesn't mean there's none. So when Jacques gave me the sample, my idea was to make in a lab a very long measurement radioactivity on this sample to make sure there's none or not. This is what I'm going to present you after. So I put the sample A on a gamma ray detector in a lab during 5.5 days. It means that during 5.5 days, the sample was on the detector, and it was counting the radioactivity gamma emitters. So this is here you have the raw spectrum of the result, and you have several peaks. The goal here is to identify all these peaks to know what they are and what radio elements you have on this bark. So you have most of them are natural elements, and you have like bismuth 214, or you are lead 214 also. So this is or potassium 40, which is totally normal. That you can find these elements anywhere in the environment, in the nature, and of course on trees. But when we zoom in the box, you have the zoom above. The left peak is bismuth 214, so this is normal. But you also have cesium 137, which is not normal at this point. Cesium is typically a presence of typically the result of nuclear activity in the world. So after 5.5 days, we have presence of cesium on the blackened sample. The question that rises after is, has the UAP contaminated the tree with cesium 137? So obviously, I did the same thing with sample B. I put it on the same detector during the same time. And as expected, we found the same radio elements, the natural one, like on the sample A, sorry. Concerning the cesium, it's a zoom in the box, and there doesn't seems to be cesium, but it's unclear. As you can see, there is a small peak, but it's not a proper one, So it's difficult to conclude here if there is a cesium on sample B or not. If there was no cesium for sure on sample B, cesium coming from the UAP could have been a good lead, but with the result of sample B, we cannot say that. Let's see then the origin of cesium-137 on Earth. So it doesn't exist in a natural state. It is a byproduct of nuclear fission. Fission of either uranium-235 or plutonium-239. So here, for this case, we have three hypotheses for the presence of cesium-137 on the bark. Either it's come from a nuclear power plant using uranium-235, or it comes from atmospheric nuclear test using both uranium-235 or plutonium-239, or it comes from the UAP. So let's test these three hypotheses. So the first hypothesis, here you have a US map of the nuclear power plants in 1966. The red crosses. I found that at the IAEA website, and as you can see, Ennisville was far, far away from nuclear power plants in 1966. I also considered the military nuclear facilities, which can use cesium in the lab, and the closest one is at 900 kilometers. So, and we know also that at that time there was no major nuclear incident in the US. So without it, a long-range contamination by cesium is not possible. So the first hypothesis is rejected. Now, the second hypothesis. Could atmospheric nuclear tests have contaminated the tree in Louisiana? First, few characteristics of deposition from a nuclear test. You have three types of deposition. You have local deposition, up to 100 kilometer. You will have tropospheric deposition, up to more than 1000 kilometer. And if the test is powerful enough, you will have atmospheric fallout all over the world through the stratosphere. Now let's focus on what is going on in a nuclear cloud for the radionuclides. It's a bit complicated, so I'm going to spend time to make you understand the graph. So when the test occurs, you have creation of a lot of types of radio elements. You will have short radioactive half-life within the first hours. Then you have creation of medium radioactive half-life within days, and long radioactive half-life within years. You have bumps like this in the graph. It means that radioactive elements are created, and because they have half-life, they are decreasing few hours or few days or few years later. That's why you have bumps like this. And according to the type of elements, they appear very quickly after the test or very late after the test. So we are in 2025. The bark was recovered by Jacques in 1966, and it was kept in a box inside a house. So after 26, it was completely protected from the global fallout after 66. So we are now 60 years later after the sample was recovered. And 60 years later, from a nuclear test, as you can see, we can still detect cesium 137 and strontium 90. Both radionuclide remain detectable in the environment. So it's almost normal to find cesium 137 on the bark recovered in Ennisville. The global fallout. There's no official study that has been released about the soil contamination of cesium in the US in 1966. Nevertheless, nowadays there are. Here's an example from Simon et al. 2004. You have the estimation of the cesium 137 deposition in the US in 2004 in becquerel per square meter. Ennisville is at the red cross, and you have the value would be between the value is between 4,000 and 5,000 becquerel per square meter. So now we know that at least in 2004, there is contamination of soil in cesium. Was it the case in 1966? We don't know. We try to figure it out. To remind you that I put this graph again, that after decades after nuclear test, the cesium and strontium remain the main residual radionuclides still measurable in the environment. I found in the literature this study from Alfred Clement, 1960, showing the radioactive fallout from nuclear weapon tests and the contamination of the soil in strontium-90 in the US. You have these isolines, which show the concentration, and the ionosphere is between both 125 millicurie per square mile and 150 millicurie per square miles. So ionosphere is more or less in the middle. So I took the value of 137 millicurie per mile. Millicurie was the old unit for activity, and I changed it into the one used today, which is becquerel, and I convert it, and it's about 1960 becquerel per square meter, and we keep in mind the order of magnitude of 2000 becquerel per square meter for strontium-90 in soil in 1965. So yes, at that time there was contamination of the soil in Ionesville from nuclear weapon tests. So probably it was the same for cesium. Here's another study from Kenneth in 2022. He shows a histogram of the frequency of the ratio between cesium and strontium in North Carolina between 73 and 77. The ratio tells us if there is more cesium than strontium in soils in North Carolina. And as you can see, most of the ratio are positive. It means that the concentration of cesium was always above the strontium concentration in soils. This is what we can see in the graph, with the curve of cesium is above the curve of strontium. So yes, probably when you have cesium, you should have strontium when it's coming from nuclear weapon tests. But we have to demonstrate it. So to conclude, if we can find strontium in samples, therefore these radionuclides are from the global fallout. We didn't perform this analysis because it's much more complicated than measuring the cesium, and by doing that you have to destroy the sample, and at that point we didn't do it. If we don't find a strontium in the sample, then more studies are necessary to prove.
So we are coming to the end of this session one with a high quality presentation, very complimentary. I think that looking at the presentation from Robert Powell on Stephen Weil, and then from Jean-Marc André and the team looking at different cases, including Stephen Weil, it means that we still have work to do, to clarify the identification or non-identification of some radar tracks. Obviously, we need cross-checking between different kind of sensors, optical sensors Alone, they are interesting, but they are not enough. Radar alone, and especially when they are 2D radars, we are still uncertainty, and the cross-checking information is very important. Now we have some kind of little break between presentation, scientific presentation, and so on. And I have the pleasure to introduce the movie which was presented yesterday evening on July 1st about Valençol 65 by Dominique Fillol. Dominique is not yet in the webinar, but he will join us later on and participate to the debate. But I can tell you by now that it's a very high quality movie, very pleasant, very real. And so I leave the floor to this short presentation of the movie.
Jeannette, il faut qu'on parle à Maurice.
Pourquoi il s'est passé quelque chose? Maurice, tu me fais peur là.
Le 1er juillet 65, à 2 km au nord-ouest de Valençol, Basses-Alpes, Monsieur Maurice Mas, cultivateur, déclare avoir vu un objet volant non identifié de la grosseur d'une dauphine posé dans son champ.
Franchement, vous y croyez, vous, à cette histoire?
Mon père, c'est pas un menteur.
Pourquoi les militaires ils sont venus?
Pour des histoires de grands.
Je t'avais dit de rien dire.
Tu crois qu'il n'y a que toi qui subis cette histoire? On nous regarde comme des bêtes curieuses dans le village.
Monsieur Mas, qu'est-ce que vous avez vu exactement?
Foutez le camp! Foutez le camp, j'en tué!
Bon, qu'est-ce qui s'est passé ensuite?
The second session is concerning mainly observation of UAP. We'll have a first paper from Dr. Laura Domine from the SCU and the Galileo project. And Dr. Laura Domine will provide us with a paper concerning the development of foundation artificial intelligence model for UAP characterization using data from a commissioned multi-sensor platform. Then we'll have a presentation from Mr. Raymond Piccoli. Mr. Raymond Piccoli is a EEF Sigma 2 Technical Commission member. He is also a member of the GEPAN College of Experts and is the director of the Laboratoire de Recherche sur la Food Lightning Research Laboratory. And the object of his paper is about the Farfadet, which is a versatile observation network for transient storm and atmospheric phenomena. To finish with this presentation, we'll have the pleasure to welcome Dr. Beatrice Villaruel from Limina Society for UAP Studies. She is a doctor in astronomy, part of the Nordic Fellow and Nordic Institute for Theoretical Physics in Sweden, and she is director of the VASCO team. And the purpose of her paper is a status update in 2025 on the VASCO and the ExoProbe projects. Thank you for your attention.
Thank you for inviting me to this webinar. My name is Laura Domine. I am a postdoc at Harvard at the Center for Astrophysics, and I work 100% of my time on the Galileo project. In this talk, I would like to describe the work we've been doing on commissioning our multi-sensor platform, which is designed for UAP characterization. And I will also explain how we plan to use this data set to train a big machine learning model, AI model, that reads multiple sensors and looks for novel classes of objects. This is work done by many people inside the Galileo project, not just me. In this slide, I'm attempting to acknowledge everyone who was involved, but I am sure I am missing people from this slide. There are two papers that we published in the past couple of years. One recently in January was published in Sensors about commissioning one of our instruments, an infrared camera array. And the other one was published 2 years ago in Journal of Astronomical Instrumentation, which described the experimental design of the Galileo Project Observatory. Measuring rare atmospheric phenomena is a good idea in science historically. In 1800, that's how we discovered that meteorites were more than a superstition. And recently in the 80s, we discovered transient luminous events, TLE, which are colorful flashes above thunderclouds that were reported many times by pilots, but only photographed in 1989, after which it became an active area of research. My hope is that the same happens for UAP. Once we start collecting scientific data about UAP, it will become an extremely active area of research, whether we find out that it is ball lightning or a technosignature or something entirely different. I am involved in two different efforts. One perspective, which is illustrated on the right-hand side, is to build portable systems to conduct targeted searches. Those portable systems are being developed at Wellesley College. I collaborate with Wes Waters there. The other effort I'm involved in, and where I spend the vast majority of my time, is a Galileo Project Observatory class system on the left-hand side, which is what this talk will be focused on. The idea is to put a lot of instruments, different instruments, in the same place for a long period of time in order to conduct census of all aerial phenomena over that location. Over time, we hope to identify statistical outliers and corroborate them. This design is described in the paper that I mentioned at the beginning of this talk. I want to start by setting the context by explaining the goal of this observatory before I move on to commissioning and machine learning, so that you understand future work in this context. We have many different instruments which are all in one location and performing a census of all aerial phenomena, whether it's man-made or natural, above that location. We are doing work to validate that census data, for example, to understand the objects that we detect as a function of atmospheric conditions. Our goal is to categorize these different objects and events into man-made and natural phenomena. And we might start to identify statistical outliers, whether they're in or outside known performance envelopes. Over time, if they become corroborated, they become outliers of interest. As long as they're outside of known performance envelope, we will keep studying them and perform targeted follow-up observations. We will share the results with other scientists, and after we formulate and test hypotheses, the hope is that we will be studying scientific anomalies. It is a long process from number 1 to number 10, number 1 to number 9. It is a process that will take years if we want to do this well. Here is a screenshot of the Galileo Project Observatory and the different instruments that are included at each site. We currently have 2 sites that have started collecting data, and we have 2 more that are planned. I highlighted in orange the sensors that will appear later in this talk. So that's the acoustics, ADS-B for aircraft transponders, and infrared camera. So this infrared camera array is the first instrument that underwent a process we call commissioning. So for any instrument at these sites, we follow a process of 4 phases. The first one is development, where we figure out what instrument we want to put out there. Then we calibrate that instrument and collect calibration data. Then we have a phase of commissioning, which can take multiple months, during which we collect commissioning data. And finally, we are in operations mode, where we are collecting science quality data, which can lend itself to UAP science analysis. It is a long process to go from development to operations and to achieve stable science quality data taking over a long period of time. So we are following this process instrument by instrument for now. And once every single instrument has gone through the commissioning phase successfully, we will declare the entire observatory commissioned and taking science quality data. Until then, instruments will be taking science quality data on an instrument basis. So what we nicknamed the DALIC is an infrared camera array. It has 8 different cameras in a hemispherical fashion. And these cameras are protected by sunshades to avoid direct sun exposure onto the sensor. Here is an example of data collected by the DALIC on the left-hand side. You have 1 image per camera that was captured at the same time. And the purple pixels correspond to the tree line, which is excluded from further analysis. So we only focus on the sky area in each camera. On the right-hand side, it is a summary of the recording efficiency per day for the 8 different cameras. So the dashed line represents where you would be if it was perfectly recording all the time when it's supposed to be. And you can see we're still far away from that line, but it is increasing over time and getting closer to that line. It is a challenge to run 8 infrared cameras pretty much 24/7 outdoors with little oversight. And we ran into many connection issues, which is part of that commissioning process to figure out how to keep the uptime as large as possible. We worked on calibration, which means how do you go from pixel coordinates in the image taken by a camera to the world coordinate system. And there's 2 different calibrations you have to perform to get there. One is called extrinsic, going from world to camera coordinates, and the other is called intrinsic, going from camera to image coordinates. For intrinsic calibration, we made our own metal chessboard because this is an infrared camera. And you take pictures of the chessboard in many different locations around the image field of view in order to extract distortion, camera gain, and so on. For extrinsic calibration, we worked with aircraft transponder. So if we know the pixel location in the image and we know the aircraft real location thanks to ADS-B transponder data, then we can extract the camera orientation, figure out in which direction it is pointing. If we keep doing this over time, then we can monitor the camera orientation over time. All of this work is described in the first paper that was published the most recently in Census. And finally, the last big calibration we did was thermal calibration. So those are infrared cameras, and intuitively, you probably think, well, infrared cameras measure temperature, which sounds straightforward. In reality, we're not looking at an object that's right in front of the camera. We're looking at objects in the atmosphere, and their thermal emissions are going through water vapor and carbon dioxide in the atmosphere. These different gases are absorbing certain wavelengths, which is what I'm showing on the left-hand side. That's a fairly old plot that shows to you, depending on the wavelengths, not all electromagnetic emissions are being transmitted at the same rate. And I highlighted in orange where our cameras are looking at. In order to account for that, you have to model the atmospheric transmission coefficient. You have to model the object emissivity, so it will be different if the aircraft is made of wood or metal. And you have to be able to relate the pixel value to target temperature, camera temperature. So we did a grid of camera and target temperature, took many different pictures in order to do that conversion. If you put everything together into the same equation, you become able to translate a pixel value in the image to a real object temperature. It is not straightforward. After doing all this calibration, we move on to commissioning process. And during commissioning, we want to build a catalog of all objects that we see. So that means we need to do object detection and tracking from the infrared videos in order to reconstruct object trajectories. We used 3D modeled synthetic images using Blender in order to train a machine learning detection model. We used YOLO v5, which was popular a couple of years ago for object detection in computer vision. And we evaluate the results of that training using manually annotated real-world images. We used about 40,000 synthetic images in order to train, and the evaluation was done on about 900,000 images. In order to track, and by that I mean figure out from frame to frame which objects, which detections belong to the same object, we use an algorithm called SORT, which is a Kalman filter, pretty much assuming linear trajectories. And that allows us to reconstruct 2D trajectories. We evaluate the performance of this algorithm using Blender again to generate synthetic videos. And we find that it breaks real trajectories on average into 3 fragments. So it is not perfect, and it is something that we plan to improve. Both the object detection and the tracking algorithm will go through improvements in the coming month. But this is a good baseline to demonstrate the commissioning process that we want to follow with each instrument. Here is an example of study that we did for this infrared camera array in order to understand how it performs on aircraft. So we divided aircrafts that pass close to the observatory into different categories. They could be in range, or they could be viewable, recorded, detected. And those categories are more and more restrictive. We define different metrics. For example, efficiency is defined as fraction of recorded aircraft which are detected. Acceptance is defined as fraction of viewable aircraft which are recorded. Then we measured these different metrics as a function of atmospheric conditions, such as visibility or precipitation. As you would expect, the better the visibility, the better the efficiency. The more rain we get, the lower the efficiency. So all the measurements we made confirmed our intuition, and we now have quantitative numbers to quantify how well we're detecting objects. What this allows us to do, for example, is to partition the sky into different bins, and for each spatial bin, we have the ability to say the fractions of aircrafts in range which are detected. As you can see, it is not, and it is far from being uniform on the left-hand side. Blue means we're not doing a good job at detecting. Yellow means we're doing a good job at detecting the aircraft. And there are many different factors that go into that plot, and we have done the work to understand every single factor, so that down the line, if we do find an object of interest, we will be able to quantify our confidence in its detection. At the end of this commissioning paper, we did an example of outlier search. We were not really looking for UAP, we were more demonstrating how we would go about looking for outliers. So we defined an outlier as highly sinuous 2D trajectories. This means it could be a falling leaf, which has a very zigzaggy trajectory. That's why I call this a toy outlier. It is not a really interesting object, but it is a good exercise to look for these objects and show how we would evaluate our results. On the left-hand side, this is an example of one video which was processed through object detection and tracking. Each color corresponds to a different trajectory, and each dot is a different detection. So if the dots are far apart, it means the object was going fast. And if they're close to each other, it means the object was going slowly. This is an example of outlier, this L-shaped trajectory, number 39. is actually a hawk if you go look at the video, but it will be flagged as an outlier by this definition. We reconstructed about 500,000 trajectories over the 5 months of commissioning. 16% had high sinuosity, and after manual review, 144 objects remained as quote-unquote ambiguous. And by that I mean they're most likely mundane, but we need more instruments and distance estimation in order to elucidate them. The paper ends with a statistical likelihood test, for which we used all of the measurements I explained previously to estimate our uncertainties and calculate how many outliers we would have if everything in the system was perfect, from recording time, uptime, to object detection and tracking. If everything was perfect, we could have detected as many as 18,000 outliers. That's because our uncertainties are still pretty high, and now our job is to work on decreasing our uncertainties so that in the future, when we do find ambiguous objects, we will be very confident in our finding. All of this was focused on one of our instruments. We have multiple, as I explained, and all of them will need to go through this commissioning process in the near future. We are also planning on adding optical triangulation in order to reconstruct kinematics. I will focus now on machine learning. We are collecting large data sets up to 0.5 terabyte per day, and the different sensors are not necessarily well aligned with each other. It is hard to label real objects in this data, and this is not a new challenge which is specific to UAP. There are many fields that are looking at similar challenges, and they're all building so-called foundation models, which mean a very large machine learning model trained on a large amount of data that has little labels. This is all work done by a machine learning group within Galileo project. So the idea is to collect data from different sensors, lots of it, and use it to train a big machine learning model using something like contrastive learning. So learning a representation of the data, which is invariant to certain transformations. After you do this training, you can fine-tune it for object detection, tracking, novel class discovery, outlier detection. So the piece in the middle, this big training of a machine learning model, is similar to ChatGPT. ChatGPT is a foundation model, which afterwards can be used for many different tasks. So one of the methods that we can use to train that machine learning model is called Dino. It is self-supervised training. What this means is you start from a piece of data, for example, an image from an infrared camera. You transform it in 2 different ways. Here, for example, I apply an orange filter and a blue filter. And you run the same neural network on each piece and hope that it learns a probability distribution which is invariant to the transformation. We did this as a proof of concept using infrared videos and acoustic recordings, and used aircraft receiver data to test that proof of concept. So qualitatively, what we show in this slide is where the machine learning model is paying attention. So remember, it was trained on real-world data without any labels, so it was never told what an aircraft is, for example. So these clips contain an aircraft, circled in red, and in the attention maps, the yellow parts indicate where the machine learning model is paying attention. And you can see, I circled in red, that it is paying attention to the aircraft in some of its layers, even though it was never told this is an interesting object. Same thing in the acoustic branch. This is a spectrogram where we have a U-shaped interference pattern, which is typical for aircraft, and we see in the attention map that this pattern is highlighted in yellow. So it is learning features associated with objects of interest, at least qualitatively. And quantitatively, we also saw that some of the features that are deemed important by this model after training correlate with real-world features, such as the number of engines of the aircraft. This foundation model will be useful for many different tasks. I'm very excited about novel class discovery, which is the task of figuring out after training that you're seeing objects that belong to a completely new class of objects. It will also be useful to develop a trigger at the edge, which means figuring out in real time whether an object that you see is interesting or not, and throwing away the data if not. This will allow us to move from recording everything 24/7 to only recording potential events of interest. And finally, we will train this big foundation model on Galileo project data, but it will be possible to fine-tune it for similar detectors, such as the small portable ones developed at Wellesley or other ones in the field of UAP studies. I will end here. If you're interested in knowing more details, please check out our papers or feel free to shoot me an email. Thank you.
Hello everyone, I am very pleased to take part once again in this webinar organized by the Sigma 2 Commission. Today, I will not present the Farfadet network itself, but rather the major upgrades of our detection and monitoring system for thunderstorm-related phenomena in the upper atmosphere. Here is the outline of my presentation. 1. Brief reminder of the Farfadet network's mission. 2. The Farfadet networks now. 3. Network evolution, the Farfadet Mark II station. 4. The Farfadet Mark II station and opening towards non-conventional atmospheric phenomena. And 5. Examples and conclusion. To begin, I will give you a brief reminder of the mission of the Farfadet network. We created this observation network 9 years ago to detect and study SPRITE, ELF, and other transient luminous events in the upper atmosphere. It is therefore a purely scientific system specialized in luminous phenomena related to thunderstorm and lightning. The original goal of the Farfadet program is to try to answer 3 simple but fundamental questions. First, are SPRITE frequent? Second, dual type of thunderstorm general SPRITE? And finally, what is the distribution of the different type of SPRITE? That is the basic premise. If we take stock of the Farfadet network now, what can we say? First of all, the deployment has been faster than expected, and we now have 13 stations operational. Next, contrary to the initial goal of deploying stations abroad, that is in Germany and Italy, they are actually located in France, with 1 station situated in Corsica Island. Finally, since mid last year, all our stations have been upgraded to the Mark II standard, which is a major development with the addition of an extra sensor, an optical sensor. Below, you can see the map here showing the distribution of the station in France. So here are the updates of the networks, the new Farfadet Mark II station. To cover a wider detection spectrum and to give substance to the collaboration agreement with the Sigma 2 Scientific and Technical Commission, we have upgraded the Farfadet station to the Mark II standards. Thus, since mid of the last year, all stations have switched to this standard with the addition of an extra optical sensor. This sensor is very sensitive and very bright, with an aperture ratio of FD1 and now records in color, both day and night, in 4K format. This upgrade is designed to strengthen the existing system by providing true full bimodality. First, with a specific sensor for sprites that is black and white, but which, of course, remain fully operational for any other type of phenomenon as before, since the sensor could film anything appearing in their field of view. Now, we also have a high-definition sensor added as a supplement, which is solely dedicated to the general monitoring of the sky and atmospheric phenomena, and which naturally complements the first one. Well, it already was, but now with the upgrade to the Mark II tip, it truly opens the way to the study of unconventional atmospheric phenomena as a whole. In summary, the Farfadet stations are operational both day and night. The network detects everything happening in the sky. It has the capacity to record and document unidentified aerospace phenomena, and this is done discreetly with scientific rigor, no speculation, but with a reliable and permanent tool. It is also about technological confidentiality and total control of the network. Indeed, this network is designated and maintained 100% by ourselves, by the Lightning Research Laboratory, le laboratoire de recherche sur la foudre. Finally, I remind you that the images are checked and analyzed daily by a laboratory analyst. So, no automated filtering, no software processing, a true old-fashioned work which guaranteed quality and rigor. And to finish, I'm going to show you a few examples. Here, for instance, you can see the passage of the commercial civilian airplane, and a little higher on the right, you will see the passage of the meteorite. Here, it is a light of two Rafale fighter jets from the French Air and Space Force. I will also point out that this kind of light produced by fighter jet during night training regularly generates public reports. Just here, this is the light. Here you have a photograph of a sprite. This sprite was emitted from about 400 kilometers away from the station. Here you have a passage of the bolide. In this video, you can see sprite captured over a distance of approximately 600 kilometers. Here is a passage of a Rafale fighter jet, also from the French Air and Space Force, on a low altitude night penetration mission. Here, I'm showing you the observation capability of the new sensor. It's a time lapse. For example, you can see the Pleiad star cluster here with all the air traffic, the small moving dots you see. You also have the star here, Aldebaran, and soon we will see the Orion constellation with its belt and M42 Great Orion Nebula, perfectly visible points, just here. This is the M42 Nebula. That's to give you an idea of the nighttime observation brightness. Well, that concludes my brief presentation. But I thought it was important to update you on the network's evolution and its enhanced detection capability. Thank you and wish you a good webinar. Thank you very much.
So I'm going to tell you about the updates from the Vasco and Exomodes. The question I'm interested in is, of course, and I think all of us are, is whether we can find artifacts of non-human intelligence. And we can do it in different ways. We can do by searching in water, in the space, on the ground, underground, in the atmosphere. I think many of you are already familiar with my work where we have been searching for stars that vanished, or we initially searched for stars that vanished, but found interesting transients, like short-lived flashes in the sky. And we were using images from the early 1950s before Sputnik and comparing to images of the sky as it looks today. And this is how I came into the UFO topic, because it started with that we found this image where you can see 9 star-looking objects that look like stars, have stellar profiles, in an image from the 12th of April 1950 that never could be found again. And we could find no astronomical explanations, no instrumental explanations. Of course, people wondering, are those plate defects perhaps? And what we thought that is that it seems to be some kind of weird objects that we could not really explain. For example, it could be reflections from some artificial objects in orbit around the Earth, but it would be in 1950. So we were wondering about if it could be reflections or emissions from non-human satellites. Because if you have something that is orbiting, that is rotating, and you have it in a geosynchronous orbit, it can sometimes produce very fast flashes, sub-second long flashes, except for that our images are from before Sputnik 1, before 1957, which became a slight trouble. So I've been telling previous times about this work when we have been using these photographic plates from before Sputnik in order to look for things that look like satellites or space debris, except for that there couldn't be any human satellites or space debris at that time. So there are different kind of predicted signatures you can have of ET probes. You can have multiple transients, but you can also have like a triple transient, or you can have multiple transients along a line. It all depends on geometry, numbers. Some things are rotating so slowly you will only see one glint. So here is one example that I also been showing you before from the 19th of July 1952, when you can see a triple transient that was there and that never could be found again, and that was published in the monthly notices of the Royal Astronomical Society. It's good to remember the number because we later will come back to that. And if you look at, in general, if you look at those along a line, which is one of the safest ways to kind of, if you look for things that are aligned along a line, you know that you're really minimizing the chance for having any sort of kind of random, mysterious plate defect that not only look like stars, but also are lying in a narrow band or have a interesting alignment. So you can see how many do you need to have in order to discard that is kind of that you're dealing with those extremely unlikely emulsion defects. And we calculated that you need at least 4 for it to be. And so here, when we did that in the past, we had like 5 top candidates, where one is the most interesting one, and one happened on the 4th of October 1954. So just to remember, this was our top candidates, and this was our absolute top candidates. And an example of the 4th of October, you can only see 3 in a line. It was, though they were very beautifully aligned, plus 1 unaligned one. So it was really kind of on the 2 sigma level. Another such example here was seen 4 in a line. This is already statistically interesting. And the best one was this one from 27th of July. So of course, those of you who love UFOs can recognize some of the dates, like the triple transient happened on the day of the Washington, D.C. flap. By coincidence, our best candidate also happened on this, and we didn't know about it. We never thought about UFOs when we found these candidates or were looking for these candidates. So this was just by pure chance. And afterwards, we were told like, oh, you recognize the dates of your candidates. Of course, it turns out that also one of these other candidates happened on the 4th of October when there was a peak of a UFO wave worldwide on the 3rd of October. So we asked ourselves then, is there a correlation? And my colleague Stephen Brule from Vanderbilt University, he has taken Vasco transients. We have 100,000 Vasco transients. Much of these transients, the 110,000, is actually false positives, because you really need to vet things very carefully visually before you can really say that this is a real case. Now, he took a preliminary database of the Vasco transients where we haven't done this visual inspection yet. So much of this, maybe 50%, one needs to throw away. However, he took this list, and he took a list of the nuclear test data set from Soviet, UK, and British tests, and he took UFOs from the UFOCAT database. So now we are having good statistical samples. And the question is there a correlation in time? Do Vasco transients occur close in time with UFO sightings also? And he did that. And indeed, he finds statistically significant on the 3 sigma level that you have actually, yes, correlations between Vasco transients and nuclear tests. One day after the nuclear test, you have 45% more likely to have a Vasco transients. Same thing you can find with UFO reports. There's a correlation between UFO reports and Vasco transients. And these are small effect numbers, but they are significant on the 3 sigma level. And this also, why this is so precious for us is because there are people who sometimes say, oh, but maybe you have plate effects. But there's no plate effect that is going to correlate with atomic bomb tests or with UFO reports. You're not going to have a correlation between UFO reports and plate effects, simply. So this really strengthens the support for that Vasco transients are actually real observations that we see. And it's an independent confirmation of the suspected correlation that we saw when we saw this Washington flap. So this is a paper we have submitted. We are waiting for the review reports. There were 10 referees declined reviewing it, so let's see how it goes. And so this is the interesting question we're working with, therefore. Is there a correlation then between the Vasco transients and the atomic bomb tests and the UFO sightings? Because correlation is not causation. However, it becomes super interesting in this case due to this timing of the events. And my is that the Vasco transients are the optical astronomical counterparts of UFO events. Now, of course, we have to demonstrate this. So what we would like to do is to, of course, reproduce the result today. But if you try to reproduce this result today, you're struggling with the problem of that we are having so much of space trash and garbage on the sky that we have all these glints from the space trash that are disturbing our sight and that are going to be mixed up with the transients we are interested in, the correspondence to the Vasco transients. So now, telling for 2 years that we have a new method to filter away the human satellites and space debris. And the good news about it is that we are publishing it next week. So for those who are interested, we will, within a few days or already next week, be able to send you a complete draft or hopefully a already accepted paper with all the entire description. So stay tuned for this. This is an example of things that you can find. If you are not, you will always have some kind of contaminant. And in our main contaminant are asteroids, like multiple asteroids that are moving in space. We are finding these are contaminating our samples, but you can easily recognize them. Here you see 2 of them, and they're moving from east to west. through the images. Here's another example of a group of asteroids moving together. So these are the contaminants with the method. We will also have a nice surprise in the article, so I think you're going to enjoy it. Just wait until next week. So when we plan to apply this technique of removing the space garbage together with the exoprobe technique, where we are using a or where we want to create a network of telescopes, because right now we have one main telescope standing there, but we want to have a network of telescopes in order to use this technique to remove all the space trash and at the same time get parallax and get information about the spectrum of an object. The goal is to detect, you want to localize, you want to verify any findings so that you see it in multiple telescopes, and you want to reproduce it. By doing that, we are not searching for UFOs. What we are searching for are specific, identifiable signatures from an EG probe or a non-human object or an unidentified artificial object. And we are looking outside the Earth's atmosphere, far outside. And if we also have a telescope that looks at the same patch of the sky when we're doing this, then we can get the spectrum of such a transient flash, because such a flash might not occur again. You might only have one timer of a half a second, and you want to get that half a second, so you can't come afterwards and examine it. So you need that spectrum when it happens. And in that way, you will be able to get the parallax of the object and say the distance to it. You will get when it happens, and you will get the location, and you will learn things about about its spectrum and its characteristics. So our main telescope is at Dartmouth, Mexico. We are running it, not automatically, we still run it manually, and we are collaborating with Space Laser Awareness that are going to help us to get a spectrum of the object. We are still missing one more telescope in order to get the parallax, because if you have these two telescopes and you get the parallax, you get the distance. And as I mentioned, we are outside the atmosphere, and we have this new method that you will get next week if you are very interested in it. Maybe it's not so interesting for you, but for me, it's very interesting to get rid of space trash. And finally, if we get the spectrum, we can learn a lot, because what if you see something really unusual? That's when it gets exciting. We want to add more telescopes because we really need at least one more. And I preferably would like several more, so that we can increase the range of altitudes or like distances from the Earth we are looking at, and we would have many more combinations of measuring parallax, which would increase the accuracy of localizing any such object. So this is the status right now. I so much wished that I could have shown today our paper, but it's just a few days too early. So that the transcript has been developed. We have it in the paper. I'm collaborating with West Waters. We have tested it, and we have actually found one very interesting object through visual inspection. The one telescope that is standing and collecting the data has so far collected 14 terabytes of data, and we keep on collecting. We are working on the fundraising for a second telescope so that we can get our parallax and run 2 telescopes at the same time, watching the same spot with our method to remove the space garbage. And I hope that we will find enough of transients to test the correlation with modern UFO sightings. So that's where we are with the exoprobe. But this is not the end of the story, because I like to search for alternative ways of finding non-human intelligence. Yes, we are in space, but I'm sure that several of you might have heard from Jeffrey that he has been on an exciting expedition this weekend. And that was to the Baltic Sea anomaly, and we're collaborating on this. So in 2011, a Swedish diver found a very interesting object, and you can see it here with a side scan sonar, a weird object on the bottom of the Baltic Sea. It's outside Åland, which is one of Sweden's what's called large islands. So it's outside there somewhere in the Finnish economic zone, and it kind of looks weird. And they kept watching it, and they found in it like right angles. It's under sediment, so it has been there a long time. It's no modern thing. You see right angles here. And you can see here is a wall. It has a wall molding. It has holes in it. It has, it just looks like a constructed wall, but who knows what nature can create. And here's another example of what it has. It has here a round hole that leads into a cavity, and around the cavity you have a square. So of course we are wondering, is this an artificial object? So there has been a lot of speculations about what that is. Could this be a non-human artifact? Maybe a crashed flying saucer? It looks like Millennium Falcon a little bit from the Star Wars. And so one of these my hobby projects is now to collaborate with Dennis, the diver, and with Jeffrey and a few more scientists, for example, from the Galileo project, in searching, examining this object with the highest resolution methods that exist in order to see whether it's a natural thing or whether it's an artificial object. Because if we would be lucky to actually find a non-human artifact, that would kind of settle the story, and we would get all the answers that we are interested in. And with that, I thank you very much for listening.
We are coming to the round table now. We are on time, which is good. And we have about 45 minutes to discuss. Well, I've maybe one question to start the debate, and then please feel free to ask a question. We have to do that, in a simple way, and just, raising hand and saying, okay, you want to ask a question to somebody, part of the speaker or the table here, but I think from the speakers it's more interesting. But before coming into that, we just welcome Dominique Filleul. We had the pleasure to show the teaser of your movie that I saw yesterday. I would like to offer you the opportunity, in a few minutes to tell your story. Of course, you are well known for a lot of people, but please, Dominique.
Thank you very much, Luc. Good evening, everyone. I'm very happy to be here just to talk a bit about Valençol 1965. As you probably know, my feature film is based on the true story of Maurice Mas, who saw a UFO in his lavender field in 1965, and saw also two beings close to the UAP. And he was paralyzed for 15 minutes by these two beings, as he said. There was trace on the soil, kind of strange hole in the middle with stuff on the earth. And for Maurice, it was a very difficult experience. He was not prepared for this, for sure, but he was also not prepared to meet the cops many times, and also all the journalists and scientists that come to him. And during his life, it was a struggle for him, and he never wanted to be famous or to get money with his story. He was a very humble man. And this is a movie about his story, the story of his family, and the story of the village also.
Okay, so I really recommend to see this movie. I just want to remind something. We met with Dominique in 2019 when you were preparing
Say flying object is secret. It's the US name.
Yes, and it was a real opportunity to participate to this project, and then we had many opportunities to meet again, and sometimes making a show on TV on Ira News in particular, and so I think it's a very, very nice movie, artistic, really explaining the spirit and what happened to this guy, Maurice Mas. We really suffered of not of the UAP by itself, but of the consequences on his life. But finally, it's a nice story. So
thank you.
Well, so we are going to open questions. I would have a question for Laura Domine to start with. You explained that you are using infrared cameras, and you made a choice of a long wave infrared spectrum. Why? Why this spectrum?
I think a big reason was cost at the time. There are many, we would like to cover everything if possible, and we do plan to add more sensors to cover, for example, a short wavelength infrared. But this was a choice done before I joined, but I believe cost was a big driver in choosing the boson cameras over short wavelength infrared cameras.
Okay, in my mind, so I was wrong. I believe that a long-wave infrared camera were more expensive than the shorter range, and
I think it's the opposite. Yeah.
Yeah. Okay. Okay. So that's a good reason. Well, however, with question marks about the radiation from UAP, very bright and so on, I think this is probably also whenever you have more money to invest in new sensors, to look at I would say short to medium wave infrared as well.
Definitely.
Very complementary.
Yeah, we definitely have to develop in the direction of hyperspectral imagery, but it is a very expensive direction to develop in. So we're starting with demonstrate that you can do this observatory with multiple instruments, which is already hard. And once we pass that milestone, we can think of adding hyperspectral capabilities, like you suggest.
And one more question concerning the station, the sensor station. So I understood that you have about 8 infrared cameras. They are connected as part of a network, or they are operated in parallel, and then you process the data to see what is happening if you have a continuity of observation between one camera to another one.
Yeah, the analysis I presented does not do instance matching, so finding the object in multiple consecutive cameras, but that is part of the process that we need to follow if we want to be very complete during the catalog.
Okay, and you are collecting a lot of data every day?
Yes, at the moment, because we're in that commissioning phase, we're collecting pretty much 24/7 data with all of the instruments, which can be between 0.1 and 0.5 terabytes a day. But we can't keep that up forever. That's why we're trying to develop these machine learning models to decide more or less in real time which data to keep. And we want that to be as efficient as possible. We don't want to miss any potentially interesting events. So it will take some work to get to a point where we're confident in these models, deploy them in the field, and stop collecting 24/7 data. The other perspective is that we want to establish a baseline of what's going on at the location. So we do want to collect 24/7 for at least a year to capture all seasonal variations, for example. But beyond that, we will try to cut down on how much data we collect.
Okay, thank you. Now, if there are other questions, please feel free.
Yeah, I had one still for Laura. Maybe you said it, but I didn't remember. How many stations do you have working at the moment?
We have one which has been collecting data for a little more than a year, and another one which started collecting data about a month ago. So total 2 which are collecting data. And it's a lot of work to go through that commissioning process, obviously, for each instrument at each location. So even though we have 2 more in preparation, I hope we don't rush into installing these because we need to make sure we understand the first 2 thoroughly.
Yeah, okay. And can you tell us the location of the station, or it's like private?
Yeah, so the first one is in Massachusetts, out in the middle of nowhere. The second one is Pennsylvania, also out of middle of nowhere.
Thanks.
Other question?
To continue with Mrs. Delnay, so I represent Sentinel Center. We have our own mobile laboratory, and we are very puzzled because we try to reproduce other teams' results. And so far, we have at least 4 and maybe 8 different tracking softwares that are being built to identify anomalies inside datasets of video images. Do the different groups talk to each other to exchange experience and programming tools? Or are each scientific group alone in his own field and trying to create a tracking software on his own?
We should all be collaborating and talking to each other. In practice, that does not always happen until you publish a paper and all the methods, and then someone else takes up the code and tries it on their own data. But I am all for more collaboration and talking to each other. Nothing we're doing is secret, and we will always improve the methods by talking more, including before publishing.
Okay, thank you.
Those are questions? I've one question for Kevin. Back to the analysis of kinematics and acceleration. Well, there are 2 ways to collect data, at least with active sensors like radars, possibly some passive ones, but it's a little bit different story. And with the cameras, like it was explained in the former presentation. Kevin, what is your feeling about the radar data collection as part of the work you are conducting with UAPX and so on to analyze UAPs? Because it's a real problem having access to that kind of data. Civil radar, of course, but there are mainly 2-dimension radars. So the problem is that you don't have altitude, as it was explained by Jean-Marc in his presentation. It's a major problem when you can't have any estimate of altitude, and that's one of the problems. What do you think about that? Is there any solution that you see on your side?
No, I agree. I mean, I think that what you don't just want speeds and acceleration. It would be more informative to have the complete trajectory in 3D, right? In 4D with the time, right? So this requires triangulation. You're going to need multiple cameras, multiple radar systems. I don't think there's any way around it, really.
To continue with Dr. Kenneth, so thank you very much for your presentation, because I just wrote an article about that very point, so now I have a scientific basis to support it. And there is a lot of noise in the scientific field about UAP science. If we go back in time, most experts said it's inside general relativity. We can explain it. We just lack the power to do it. And the further we advance in time, scientific publication or comments by scientists working on UAP say that they need a new physics, they need new law, they need a breakthrough discovery that can explain everything that they see inside UAP data. What is your point of view on that? Is general relativity sufficient, or do we need a breakthrough in physics?
I don't think it's clear yet. I think we haven't collected the data to be able to decide what the situation is. If general relativity is in play here, which could explain the accelerations, you should see other effects. You should be able to see warping of the light around the object, due to gravitational effects. You should be able to detect these gravitational effects. Ideally, it would be great if we could get data from gravitational wave detectors like LIGO, but they won't supply data and they won't supply unfiltered data. So the data is already being filtered to exclude things like what we would be interested in. The other thing you would really want to do is if you hypothesize that they're using something like warp drive, then you need to be able to test for that. So you want to be able to detect spectra and look for redshift and blue shift, and redshifted light and blue shifted light from the objects to verify that you've actually got some kind of warp drive going on. And if that's what's going on, you would want to be able to identify the kind of warp drive. I mean, what are they exactly? How are they warping space-time? And that's something you would want to know. So I think that there's a lot more information that we need to be collecting.
Thank you.
Oui, bien sûr. On the speaker side, feel free to ask questions, okay? It's not only people here in the EEF, headquarters. Feel free to ask questions.
Do we have Mr. Piccoli on? I don't think so. No. So for Dr. Villarreal, if I remember well, you are part of the ECRI.
What?
The European Crash
Yes,
Retrieval
yes,
Initiative.
yes.
I had a question for that because as we have a mobile observatory and laboratory, did you design a scientific protocol to recover the possible debris you could detect?
We haven't done that yet, but when we are now working with the Baltic Sea anomaly, our goal is to design the best procedure on how to examine such a potential crash. Let's say we don't know what it is. We don't even know if it's a true anomaly at the moment. We want to find out. We have this interesting case. We have all this new data. And now what we want to know is is it an anomaly? Like a true anomaly? Is it what kind of? And are there signs of that it's artificial? And if it's artificial, of course, you want to know, is it a spaceship that crashed in there or not? And while doing this, we want to learn the best practices and what kind of methods have to be used or developed in order to efficiently decide if something is a crashed UFO or not. And also while doing that, what I hope it can lead to are ideas for how to actually scan the ocean floor for real examples of, or not, not saying anything about this, but for more examples of potential crashed UFOs. And that's my hope, is that this first example that we will have with the Baltic Sea anomaly can teach us all these methods and the thinking and how to actually do this, because I don't think it has been done before. I think the story with Avi Loeb's spherules is quite different, but here we have an opportunity. So it will be a first case how to work with crash retrievals, potential crash retrievals. So it's super exciting, and it's cross-disciplinary, interdisciplinary, everything, and super, super exciting thing to do as a hobby thing on not my main project, but of course super fun. So we're working with Jeffrey on that, and we're working on thinking about all these experiments. You can ask him more.
Perfect. And I have another question. It's about the scientific standard of what could be considered an artifact coming from a non-human intelligence. Did you design a specific set of variables that an object needs to fit to be determined to be of non-human origin?
Not yet, but we're talking about it with SUAPs about how to work on that, because there are so many things that have to be done. We need to really develop protocols. We need to develop signal. I mean, get clear ideas of what to look for, how to look for it, what counts as evidence, what counts as secure evidence. There is a complete protocol that has to be done. It has not been done. So this is something that needs not only us to examine the Baltic Sea anomaly, but it needs a complete community to look at it and come with ideas, brainstorm from all possible directions, from all fields, from geology, from oceanography, from astronomers, people who work with archaeology, people who work with material science, material physics. You need so many different disciplines to look at one object and tell us, how do we do this? And we're just taking now the first baby steps into a completely new type of science that has never ever been done. So we will need lots of help and support with it.
Yes, absolutely. And I give you a pet theory of mine. I had the opportunity of handling real debris from a UAP case, and it was very similar to some metal-based meteorites that were exposed in New Zealand. So I wondered to myself, in actual collections inside New Zealand, some meteorites that have been identified as metal-based may be UFO debris, but as no in-depth analysis has been made at atom level, like we talked a year ago, that could be a really easy way to find debris that hasn't been exploited before.
Exactly, and maybe we should actually search the deserts, like Sahara and all these places. That's where you will find easily things.
That's all for me.
No other question? Okay, so I'm very impatient to see other presentation and certainly some results about your submarine recent exploration. I would like to thank you warmly for the work that you have done to prepare this webinar quickly, because we announced that, well, 1 month ago, so we had maybe a little bit more, but we had a short period of time to prepare this, and this period of time is very busy. It was my case, and for others I know as well. So thank you for your friendship and the quality of your presentation. I really hope we will have many occasions to exchange. And I say that for ICU. Robert Powell was not in presentation, but it was not physically there. I really hope that we will continue to share cross-analysis, and especially on some case like Stephen Weil. We made an inventory of the class of radar returns and so on. There are some which are strange. We will continue, but as Jean-Marc said, if some events happen below the bottom of the radar coverage, it's difficult to find, in this case, explanation because we don't have the data. So that's, as usual, the problem of civil radar, military radar, and what could be obtained as additional data coming from the area of military assets. But of course, it's not in the street for free. So wait and see. Thank you. I think that we can close. Pierre. Yes, of course. Excuse me. Please.
Yeah, thank you very much for all your presentations, which were excellent, very impressive. And before concluding, I'd like to highlight a few items, 3 of them, in actual fact. The first one is that there is less secrecy from governments on this topic of UFO, which is a good thing, and especially from the US. They acknowledge the issue and the fact that we can work on it. That's a good thing. But those governments usually said that since there is no danger, apparently from these UFOs, they started discarding it. So I'm not sure that their communication also open any longer. The second item is that we've, along the years, found new explanations on some UFOs, as was mentioned earlier on by Laura Domine. There was Bio, initially 2 centuries ago, with the meteorites. More recently, we identified that some of them were sprites. That was also highlighted in one of the presentations. One which may not be well known is from Japan, who found out recently that some of the pictures that some people see are in actual fact projections from their own retina. And that's a fact that has been demonstrated now. And the third item I'd like to stress is that there are a few more things that are not explained, and it's very important that we share our experience and also our own capacities. And we definitely show that this type of webinar does it. I've very scarcely seen so much exchange, with somewhat in the workshops that were organized by the Japan, Kaipen 1 and Kaipen 2. We also saw many exchanges, and that is very good, and I hope we can go further. Now that the Americans have started discussing the thing, or at least showing that they want to discuss it, maybe it's becoming a more serious and more important item. I don't know what you think, but when the Americans speak of something, it's becoming important. So hopefully they will not back off and do a bit more about it. So what was highlighted by Luc Denis, and I will end up with this, is that we need to exchange more, collaborate much more, both worldwide with all types of people working on this thing, and also more technically with scientific exchanges. We've had very good examples on this on session 3, and as I said before, the exchanges were excellent, and I hope we can go much further. And before I end up, you may know that, and I hope that the Americans will speak up a bit more. We saw this seem to be keeping things secret. That's a good, UFO is a good item to keep secrets. But hopefully they may talk a bit more. You may know that NASA a while back went to Japan and Toulouse to ask them what they did and how they did it. And that helped us to go back to ARO to tell them, because they were not part of ARO, and they spoke to ARO and said, look, maybe we can help in few cases, and this is what we could do. That's a good thing that happened. And it's important to know now that ARO itself has contacted Japan, and they want to meet them very, very soon. So maybe the Americans will open up, and we at AAAF, and especially with Luc Denis and Commission Sigma, are very happy to be part of this dynamics to really share and open up the discussions on this UAPs. Thank you very much.
Thank you, Pierre, for this very good summary. Well, we will see which are the next opportunities to speak and to exchange. Well, we will see maybe opportunity like Seoul with invitation. We will see, but we are really sticking to the scientific and technical approach, of course, with expertise coming from the civil domain, but also the military domain, for sure. And really opening the spectrum, it's not only looking at the sensors, but looking at the effects, the microwave effects and all that stuff. And I think there are different alleys of analysis to share together and to improve our knowledge from the old cases and from the recent ones, and maybe for the new ones that will be created thanks to this instrumentation that you are describing. Okay, so I propose we close this meeting. Thank you to all, and see you next time. And if there is on your side any opportunity of conference, to participate, please let us know. Thanks.
Okay. Thank you very much.
Thank you very much.
Thank you. Thank you.
Merci Baptiste pour ta patience.
Thank you.
Merci Jean-Marc. Thank you to all.